page. I record this too. So I will be there tomorrow, and I will be there Monday, and then I won't be there Tuesday or Wednesday, but then I will be there Thursday and Friday next week. So yeah, let me kind of, before we move on to that, let me scribble that down. So I'll put on campus. So again, I will be there tomorrow. I always forget how many M's are in tomorrow. Anyways, tomorrow, Monday, Thursday, and Friday next week. So if you have any questions or anything, or want to give me stuff, that's fine. Times I'm off campus. So that'll be what? So Tuesday and Wednesday next week. Tuesday, Wednesday. After today, obviously. So yeah. So good. Those. And today we're going to finish up this chapter, so I'll post another homework for this chapter, just give you more work to do. So it'll be great. So anywho, so yeah, so let's finish off this chapter and talk about the energy time uncertainty relation. So before we talked about the uncertainty relation is built in by the commutation relation, saying that the uncertainty in some operator A times the uncertainty in some operator B, not A again, having one of those days, is then greater than or equal to, what was it? So it was 1/2 of the modulus of the expectation of some other operator C, where C was equal to, or at least I times C was equal to the commutation relation between A and B. Okay. So when it comes to operators, this is actually where the uncertainty relation comes from. And we're going to see this when we actually start talking about position space and momentum space and all that kind of good stuff, and see where that famous uncertainty in X times the uncertainty in momentum is equal to H bar divided by 2, right? At least greater than or equal to that. So this one comes from here, but this one, the energy time uncertainty relation, actually doesn't come from this. It actually comes from something else. And it comes from basically the idea of when does a time evolved state no longer resemble its initial state. So resemble the initial state. So basically meaning that it has evolved enough that it no longer looks anything like its original state. So when is it, so the energy time uncertainty relation basically comes in from when it starts to no longer look like itself. So when the time evolved state no longer starts to resemble this initial state. So the way we're going to kind of quantify this is to talk about something else, which is a what's called the correlation amplitude. So let's talk about correlation amplitude. How many L's are in correlation? 1. Okay. Amplitude. So correlation amplitude, we're going to call that C of t. So correlation amplitude is time dependent, is then equal to the interproduct between the state at its initial time and the time evolved state. So this is, we're going to call the correlation amplitude. And this thing in other contexts is also what's known as the 2-point correlation function. 1L. There we go. Correlation function. And I'll describe that for other things as well. Stop it. Which in our case is then equal to the, basically it's equal to then the expectation value of the evolution operator, right? So this is basically what the correlation amplitude is. So this is basically, yeah, the expectation value of u of t, right? It's basically what this thing is. So things like correlation amplitudes or 2-point correlation functions are used in physics basically all the time. what they basically tell you is how do 2 points, whether it be position or time or angle or anything else, how much do they relate to each other? So what do they actually look like? So how is one point correlated to another point? So for example, if I was talking about in cosmology or in astronomy, if I was talking about, say, the CMB. So if this was the CMB, the cosmic microwave background, so a lot of times we use what's called the 2-point correlation function, which basically says that if I take some point here at some angle, right? So this is some point, and then I choose another point basically over here. And so that these two are separated by, say, some angle of theta, then in this case, the 2-point correlation function C theta then basically tells you how this point over here correlates to this point over here. Right? So if this is 0.1 and this is 0.2, then this thing called the 2-point correlation function basically tells me how related are these points. And then basically what you would do is you would integrate over the angle to basically tell you the correlation of the entire space. So this is basically how we have things like the flatness problem and the horizon problem and things like that. Basically, this is where one of the ideas of inflation kind of came from, saying that it turns out by the CMB, this point here is very highly correlated to this point over here, even though they're at a huge, tremendously separated spatial distance. So the only way that can happen is if these things were in causal contact initially when the universe was basically formed, right? Because otherwise, to have that this spot here and this spot here are anywhere nearly correlated to each other when they are nowhere in causal contact, there's no reason for that to actually be true. So this is why one of the ideas of inflation is that we start off with something small and then inflated the hell out of it. So initially everything was in causal contacts, but then when it got to something very large, in that case, then this point over here and this point over here, which are no longer in causal contact, I can't really send a photon from here to here anymore, but these guys have the same temperatures and same anisotropies as this guy does, because originally they were in causal contact with each other. So this is the same idea here. So basically what we're looking at is we're kind of asking the question of how much related then is the time evolved state to the original state. Okay. So in this case, we're just doing a 2-point correlation function in time as opposed to space, right? But basically it has kind of the same idea. So, great. So again, this is a measure of the resemblance of the time evolved state to the initial state. Okay, so that's what we can kind of think of this thing as. Good. Now, let's look at a special case. Let's see kind of what this thing means. So our special case we're going to look at is the following. So let's say that the initial state is an eigenstate of the Hamiltonian. So we're going to say that this initial state psi 0 is an eigenstate of the Hamiltonian. Okay. So in this case, then our correlation function C of t is then going to be equal to psi 0 u t0, and let's say that the Hamiltonian is also time independent, just to make this a little bit easier of an argument. So Hamiltonian in this case is not time dependent. So in this case, we can write this then as psi of 0 e to the minus I h t divided by h bar, psi of 0. Now we're going to act this guy onto this state. But again, since this is an eigenstate, then that means that just pulls out the energy of this particular state. Right? So this is then going to be equal to what, psi of 0 times n e to the minus I. I'm just going to call that e sub n t divided by h bar. Psi 0, but now this is just a number, which means it comes out of this correlation function. So this then becomes e to the minus I ENT divided by H bar. Size 0, but size 0 is simply 1. So this is then e to the minus I ENT divided by H bar. This guy is just equal to 1. So what this means then is that in this case, the correlation function basically just rotates around when it comes to time, but the modulus squared of this guy then is simply equal to 1. So in this case, in the special case where what the initial state is an eigenstate of the Hamiltonian, then that means that it has 100% resemblance. So in this case, the modulus then of our correlation function is equal to 1, which means that the time evolved state is 100% equivalent to the original state. So this thing has 100% resemblance. So these two are exactly the same states. Cool. Now, in a more general situation, what we're typically going to do is, as we've done before, we're going to what? Evolve both of these in terms of some other parameter, right? So let's do a superposition over some ANs, right? So let's write C of t then is equal to, so let's do it this way. How do I want to do this? I guess I'll do it this way. So this would be the sum over n of Cn star AN, right? Times then the sum over m of Cm AM, right? Times e to the minus I EMT divided by H bar. Okay. So this then is going to be equal to the sum over m and n of then Cn star Cm e to the minus I EMT divided by H bar, inner product between AN and AM. But this guy is simply equal to delta and m. So if I take a sum over this, that portion is going to cause all of the n's to be equal to m's or m's to be equal to n's, whichever sum you want to do. So this then becomes simply the sum over n of then Cn modulus squared e to the minus I ENT over H bar. Okay. So in a more general sense, what will happen then is that our correlation function will be the sum over all these Cn's e to the minus ENTs, right? Now, one thing that'll happen though is because of this exponential term, what'll happen is, remember, the exponential is sines and cosines, which basically means that when I write this out, each one of these different Cn's will then have a different energy, which means that we're going to get both constructive and destructive interference. So in general, what'll happen is this will lead to both constructive and destructive interference. Which means that when it's constructive interference, and these guys are going to be very similar to each other, as opposed to when it's destructive interference, that'll cause it to go to 0, which means that they're not similar to each other basically at all. Right? So in this case, what we should expect then is that as time increases, this thing is going to decay, right? So basically, because of this, what we should expect then is that C of t, in the limit that t goes off to infinity, this thing then is going to approach 0. So this thing is not going to resemble, so the final state won't look anything like the initial states in a more general sense. Okay. So if we want to estimate how quickly this thing does it, or when this thing actually loses its identity, what we can do is we can move to the fact that, let's say that, we have a superposition of actually energies. So we're going to write this as a superposition over energies, where each one of these energies is very close to each other. So over energies, which are very close to each other. Now, what that will do is, since each one of these energies is very close to each other, what we can do is we can look at this then as a quasi-continuous distribution. So this would be, I'm going to say, quasi-continuous distribution. Have you both taken thermo?
No, I have not.
You have not yet? Okay. And Clayton, you did before, right?
Yes.
Yes. Okay. So remember in thermo, so if I had energies which are all discrete, but they're very close to each other, as long as you take your kind of reference energy to then be something bigger than this, then this thing looks as, instead of being a discrete distribution, it's actually going to look as a continuous distribution. So if I say my difference in energies is, you know, this width, then basically a whole bunch of energies, even though they're discretized, shows up on the inside. So then you turn a continuous distribution then into a a discrete distribution into a quasi-continuous distribution. So that's basically all this means, is even though I have energy, say, across this axis, as long as I take my difference to be basically bigger than the separation between these discretized energies, then we can make this thing quasi-continuous. Okay. So if we take it to be quasi-continuous, what that means then is that our sum over n then is going to be replaced by the integral over the energies of the rho here, where rho then is the density of states. So basically meaning how many energies are packed into some sort of location. Right? The other thing is then our CNs, which here were simply constants, these things are actually going to become functions of the energy evaluated at whatever energy they're evaluated at. So each one of these CNs then are going to become functions, but each CN is actually evaluated at some particular then energy. Okay. So under these replacements, what this means then is that our discretized, so let's write that down again, which was then equal to the sum over n of Cn squared e to the minus I Ent divided by h bar, is now going to be replaced by the integral of dE rho e, and then I'm going to get a GE modulus squared times e to the minus I energy times time divided by h bar. So basically going from the discretized to then the quasi-continuum, I'm now going to get something that actually looks like this. Okay. Where this thing is normalized, where the normalization is that what the integral of dE rho of e times then the modulus squared of GE squared has to be equal to 1, right? So this is our normalization condition. Normalization. It's raining outside. Yay. So this is our normalization. Now, in practice, what'll happen is pretty much our system is going to be peaked at some sort of reference energy. So in practice, what'll happen is that our system is peaked. I know how to spell. There we go. Our system is peaked at some energy. Let's say E is equal to E0. Okay. So basically that reference energy will then give us the greatest contribution to this particular integral. Okay. So, but that integral will then also have some sort of width to it. And let's say that this then has a width of delta E. Okay. So what does that mean? So that means if I plotted the integrand of the integral, right? So if I have the, would you stop doing it? I hate it when it does that. Okay, so if I plot the GE modulus squared times the rho E versus the energy, what happened then is that this thing will, that is a horrible line. Hang on. Let me erase this. Make this look pretty. Make it look pretty. We can do better than that. Okay. Almost a straight line. There we go. Okay, that's better. So good. So if I basically plot this thing, it's going to be what? Very low initially, and then it'll increase, reach its maximum value, and then kind of decrease away from there. So this will happen at the reference energy of E0. So this is where it reaches its maximum. And then this thing has a width, which is half maximum of then delta E, right? So this has some sort of spread of delta E. Guys doing okay? Good. So taking into account that this thing has some sort of peak, we're then going to rewrite our correlation as then being equal to e to the minus I E0 t divided by h bar times the integral over the energy of the density of states times the modulus squared of these amplitudes times then e to the minus I times the energy minus E0 times t divided by h bar. Okay. Keep hearing running water on one of your guys' side, but that's fine. Good. Guys doing okay?
So far, I think so.
Good. So we've seen things like this before in math methods, right? So basically, this thing is a what? Fourier type integral. And what we said before was that this Fourier type integral, because of this exponential term. So if I'm looking at this thing is going to oscillate, which means that if I integrate over this oscillatory term, all of this is going to average to 0. But now we know this thing is peaked, so it's going to get peaked then at this E0. And then after that, it's going to drop back down and then basically average the 0 again, right? So the integral for something like this during this region is going to average the 0. So I don't know why I just wrote an S. There we go. So basically, that means that CT will then average to 0 in this region. In this region, CT will also average the 0, which means that basically we're only going to get the contribution in this region here, right? Where again, this thing is focused at some E0. Now, we're not going to go through all the same arguments that we did for there, where we actually chopped all this stuff off and then approximated what this integral is. But basically, we're just going to go kind of through the argument of this location here. So again, since this thing is peaked, our major contribution is going to come from the fact that E minus E0 has to be kind of equivalent to this value here, right?
Hey, Professor.
What was that?
Oh, I know that. What you guys working on?
Quantum mechanics. Do you need me to leave?
Is that Scheller right here?
Oh, I didn't know that. No, I didn't post it. Does he know you're here? You got your camera closed.
Hold on just a second, Professor. Change rate. Yeah, I've got the camera turned off.
Greenwood, why don't you teach him something useful?
I am. I'm telling him how to approximate an integral.
I like that. Are you using Green's function or?
No, this is just a density of states. So we're just making an argument that this is for the energy time uncertainty relation, basically. So that this is only dominated by this term when E is close to E0. That's basically about it. So.
And the width of that peak is that a time? What's the horizontal?
Oh, in this case, right.
Yeah.
So this has a peak across here. So this has a width of delta E. And then across here, I'm just E in this case. Yeah.
Okay.
Yeah.
So delta E, delta T.
That's right.
Yeah. Okay. I'm
Exactly.
reminding myself of what I forgot.
That's
all
right.
Righty. I'm gonna shove him into the next room.
Okay. Sounds good. Why? What do you got going on over there?
I got I got 107.
107 now. Gotcha. Cool.
You're welcome. Oops. Sorry about that, Professor.
Oh, you're fine. Let me know when you're situated.
Yeah, I just have to get my notepad here.
Okay.
Okay.
Clayton, where are you at right now?
In my apartment.
You're in your apartment? Nice.
Yeah.
So nobody's going to kick you out.
Unless the cops show up.
Nice.
Okay, let's see here.
All right. So good. So let's go back to what we did in math methods. So again, what we said was that what? For this to have a dominant contribution, what has to be true is that this value here must be small compared to this value here, right? Or at least the inverse of this value. So, because again, remember that we are looking at those when those things go to infinity. So basically, and this thing has dominant contribution when e minus e0 is small compared to then h bar divided by t. So the characteristic time then that this thing is going to start to lose its identity then is when t is approximately then equal to h bar divided by delta e, where delta e then is equal to the width, right? So basically, why do I know it's the width? Because if e minus e0 is say smaller than delta e, then I'll get no contributions to this integral. So basically what will have to be true is the dominant contributions come when e minus e0 is about the same size as delta e. So here I'm just simply going to replace the e minus e0 with then delta e. So basically, or if I call that delta t, doesn't really matter how I want to call it. So basically this thing then starts to lose its identity in a characteristic amount of time when then delta e then is approximately equal to h bar divided by delta e, or, which gives us then our uncertainty relation, that then delta e times delta t is then approximately equal to h bar for when this thing actually starts to lose its identity. So the correlation function then will start to decrease when delta E times delta T is approximately equal to H bar. Okay. So this is actually where the uncertainty relation, this uncertainty relation comes from. So it comes from the fact that the correlation function here basically starts to go to 0 when this thing starts to occur, right? So basically anything greater than this, the correlation function is basically going to go to 0. So when delta E times delta T is greater than like H bar, then basically the time evolved state then has nothing to do with the original state. So it starts to actually lose its identity when these two things are approximately then the same. So this is the energy time uncertainty relation within inside of quantum mechanics. This is where it actually comes from. Like I said, unlike the momentum position uncertainty relation, which comes from the fact that what you have two non-commuting observables, but in this case it actually just comes from this thing now starting to lose its identity at this stage where this integral is sharply peaked. Okay. You guys doing okay?
I think so.
Good. Okay. So good. So that's it. That's the end of this chapter. So now we're going to start chapter 7. Okay. So chapter 7, we're going to start looking at multiple states. So basically, what we want to start looking at is what happens if I have, say, a state created from two other states, which basically means that, for example, let's say we're looking at something like the hydrogen atom, where I have a proton and I have an electron. So I want to know, how do I actually describe this state, which is actually two separate particles which have their own different state vectors to them, right? So again, if I wanted to describe the spin up, spin down, so let's say I wanted to describe the SZ behavior of each one of these guys, right? So this one's going to be described by plus or minus Z, and this one is also going to be described by plus or minus Z. So now I have two particles, so I have two particle states, but I want to describe a single state in terms of these two particles. So this is basically what we want to know. So good. So let's start off by reminding ourselves. So plus or minus Z is shorthand notation again for the spin equal to 1/2, and then the M value equal to plus or minus 1/2, right? So that's what this guy is. So if I have these two particles, let's say particle 1 is the proton and particle 2 is the electron, then in this case, I can say plus or minus Z for particle 1, then deals with the spin of particle 1 and the magnetic number of particle 1. So, but since the hydrogen atom itself, so the hydrogen atom is a combination of these two, then I have to describe both particles simultaneously to be able to fully describe then the hydrogen atom. So a natural way that we can actually do that is we can say, well, we have a total state, which is made up from the spin components of the first particle, along with the spin components of the second particle, M2 equal to plus or minus 1/2, which then gives us a total state, which is then going to be plus or minus Z plus or minus Z. And we'll talk more about what this thing actually means in a second. So here, what we're doing is we're describing each individual particle. So this first part here describes the spin components of the first particle, where the second part here describes the spin components of the second particle. So here it's just saying that this is spin up. So S1 equal to 1/2, and then M, the Z components or the magnetic number, then is plus or minus 1/2, and then same thing for this guy. So that means possible combinations we can make for these two would be, let's say the first one is spin up, the second one is spin up, so this is 1. The first one could be again spin up, or the second one is spin down, so this is another possible state. Or the first one is spin down, but the second one is spin up. Or finally, we can also have that they're both spin down, right? So these are possible states that we could actually have. So in this case, these would be then my basis functions for this composite state. Now, of course, this is not the only way I can do this, right? So I can say, I can look at the SZ component for the first particle, say for the proton, but I can also then look at the SX for then the electron. So another possible way I could say this is, well, I could also have one state would say positive Z, and then the other one is with positive X, for example. Or I could have positive Z with negative X, or I could have negative Z with positive X, or I could have negative Z with then negative X, right? So these are other possibilities that we can actually have, right? So I'm not just relegated to the fact that I can have to talk about the SZ for both of them. I can actually talk about SZ for one of them and then SX for the other one, right? So I don't have to necessarily talk about the same directions. Now, but this one here, the SZ with the X is actually related to SZ and SZ by the fact that, remember, X by itself is equal to 1 over the square root of 2 of Z plus minus Z, which means that I could actually rewrite this spin combination in terms of Fz for both of them as 1 over the square root of 2. And in this case, I would then have a what? Z with a plus Z minus Z. Right? So in this case, this would be my spin vector for this guy. Make that look prettier. There you go. Z minus Z state there. Okay. That's okay.
This couldn't get any more interesting.
What's that?
I said this one I thought things couldn't get any more interesting.
It'll get much more bizarre. Don't you worry about it. Okay, so notice one way I can actually make the states is I could start off with the original states. So let's say I have both of them ZZ. I can actually get to this state of ZX by simply rotating the second particle. Right? So amen? Okay. So I can actually get this second state from this state by doing a what? Counterclockwise rotation. That's a clockwise rotation, isn't it? Counterclockwise rotation of pi over 2 about what? The Z axis, right? No, I'm going from Z to X, so that's about the J axis. All right. So basically what this says is even though I have 2 different spin states, right? So let's go back. So I have the spin state for the first particle, which again may be the proton, and then the spin state for the second particle, which may be the electron, if I'm talking about something like a hydrogen atom. So what we can do is we can actually rotate the spin of one of those particles while leaving the other one alone. So basically what this ultimately applies to me then is 2 things. Number 1, that I'm going to have generators of spin for each one of these 2 particles individually. And as long as these 2 particles are not interacting, these 2 spin generators are going to commute with each other because I can rotate the one without rotating the other one. Okay. So basically this tells me 2 things. So again, number 1, we're then going to have spin vectors for the first object, which will be what? Spin x1 in the I hat direction plus spin y1 in the j hat direction plus then spin z1 in the k hat direction. So all this is for the first particle. Simultaneously, I'll also have its own generators of spin for the second particle. So I'm going to have a spin x2 in the I hat plus a spin y2 in the j hat plus a spin z2 in the k hat. And as long as these guys are not interacting, so if there are no interactions, whoops, which may or may not be true, in this case, what will happen then is that the spin vector of the first will commute then with the spin vector of the second. Meaning again, that I can rotate the one without rotating the second one. So as long as these guys aren't, for example, entangled to each other, I can rotate the one without doing anything to the other one.
Would that work in this particular case, Professor, like with the hydrogen atom, or would that?
I'm sorry?
I said, would that work in this particular case with a hydrogen atom?
You want the easy answer or the complicated answer?
How about the easy answer?
The easy answer is as long as I am looking at simply something like the ground state energy without corrections, the answer would be yes, this would work.
Okay.
But if I'm looking at the corrections to the energy due to spin couplings and relativistic effects and perturbation theory, the answer is no.
Okay.
So, yes. So it just depends on how I'm actually looking at it. So yeah, so if I'm looking at something that's highly coupled together, so something like a hydrogen atom, the answer ultimately would be no. But if I just had, 2 particles that I wanted to describe where, say, they're spatially separated, so they're not actually interacting with each other, We'll talk about the interaction for the hydrogen atom in a minute. So in a hydrogen atom, it's a little more complicated because you're getting interactions due to the spin-spin coupling, which is the first thing we're going to look at. And the reason for that is, again, if you think about the proton has a magnetic moment, which basically means it has, you know, a magnetic field. And then the electron, which is sitting out here, has its own magnetic moment. Let's say it points this way. So this magnetic moment is interacting with the magnetic field at this point, right? So say his magnetic field is pointing this way. So this is then at an angle of theta. So here I'm going to get a coupling between the magnetic moment of the electron and the magnetic field from the magnetic moment of the proton, which is basically what gives us what's called the fine structure. Yeah. So anyways, this is what's known as a spin-spin coupling, basically. So in that case, if I ignore the spin-spin coupling, which gives me corrections to the energies, primarily the ground state energy and any other energy, then this is actually satisfied. So if I ignore things like this. Now, the overall thing is I can mostly ignore this because this interaction, again, we're going to talk about this very soon, this is a ridiculously small correction. So this is a very small correction, which means that it does actually split the energy, but it doesn't split it by much. So this is why this is called the fine structure. So even if I kind of took something like this into account, since the correction is so small, this thing won't be exactly equal to 0, but it'll be close enough to 0, so this would still be satisfied. So meaning I could still rotate the spin of the electron without really doing much to the system. So I wouldn't really do much to the rotation of the proton. And that's mostly because the proton is, what, 2,000 times heavier than that of the electron. So I could rotate the electron without actually doing anything to the proton.
That's kind of what I was wondering about.
Right. Good. All right. Everybody's okay? Good. Now, if they do interact with each other, but if they do interact, then this won't be true anymore. Again, in general, which basically means that the Hamiltonian won't be diagonal in that representation. In the basis functions that we wrote down before, in the basis functions. So in that case, basically what we'll have to do is we'll have to do what we've done before, which is diagonalize the Hamiltonian and then find the basis functions, which then will diagonalize that Hamiltonian. So if this is true, then here we'll have to diagonalize the Hamiltonian and then find linear combinations of the states to diagonalize it. So that'll basically be the only difference there. So basically meaning in those basis functions that were down, the z, negative z, negative z. And knows that it won't actually be diagonal in that representation anymore, but we'll have to find linear combinations of those states that will actually diagonalize then the Hamiltonian. And we've done that enough at this stage that we know how to actually do that. So good. Guys doing okay? So the next question is, what does this notation actually mean? So when I wrote down plus or minus z, comma plus or minus z, the question is, what exactly do I mean? So what what does this mean? So we never formally use this word now that I actually think about it. But basically, plus or minus z, again, lives in a complex vector space. A complex vector space. And the name of that vector space is what's known as a Hilbert space. So basically, if I'm looking at this, what will happen then is that this particle here lives in a complex vector space, i.e. a Hilbert space of his own. And then this particle here lives in his own complex vector space, again, a Hilbert space. So basically, if I think about drawing this out, what will happen then is that what? I have these basis functions. So again, let's say this is the positive z direction, this is the negative z direction. So this is the Hilbert space for particle 1. Simultaneously, particle 2 will have its own Hilbert space, which again is this complex vector space, I, that he lives in. So what this thing actually means is it's saying that what I'm doing is I'm taking this complex vector space and pasting that complex vector space on top of this vector space, making it a larger vector space. That's ultimately what this thing means. So what this means is we're doing a new type of special mathematics, which basically says I'm going to take this guy and paste him to him, and simultaneously take him and paste him to here. So effectively what we're doing is we're taking these two one particle vector spaces and pasting them on top of each other. In mathematics, this is what's known as a direct product. So when I write down plus or minus z, comma, plus or minus z, what we really mean is that this is equal to the plus or minus z for the Hilbert space of particle 1, tensor product or direct product with the Hilbert space spin components for the second particle. Okay, so this is what we actually mean. So this notation here means this. So again, what we're doing is we're taking this complex vector space, this Hilbert space for the first particle, this complex vector space for the second particle, his Hilbert space. So again, this is a one particle Hilbert space, this is a one particle Hilbert space, and then we're pasting those two Hilbert spaces on top of each other to now create a new Hilbert space, where that Hilbert space now is this direct product of these two spaces on top of each other. Okay. Which basically means that this Hilbert space here has 2 degrees of freedom. Right? So this is a 2 degrees of freedom. This one also has 2 degrees of freedom. So this is 2 degrees of freedom, which means that this is 2-dimensional, this is 2-dimensional. But when I paste these on top of each other, I also have to paste the dimensionalities on top of each other, which means I'm taking a 2 degrees of freedom times the 2 degrees of freedom, which gives me a total of 4 degrees of freedom. So this thing then has 2 degrees of freedom times 2 degrees of freedom, which then gives me 4 degrees of freedom. Okay. So basically what we're doing again is this notation, even though it looks similar to a notation that we wrote down before, this is completely different. So I'm taking a particle which lives in one Hilbert space, particle that lives in a second Hilbert space, pasting these guys on top of each other, which is now increasing the dimensionality. Okay. Where's your mama?
She left.
She left again? Okay. Well, why don't you bring mommy's computer upstairs and sit here until I'm done, and then I'll turn on the TV, okay?
No. I want you to turn on my mom's computer.
Okay, we'll bring the computer and I'll turn it on. So good. So sorry about that. So in this case, if I have 5 degrees of freedom here, 5 degrees of freedom here, I paste these on top of each other, I now have like 10 degrees of freedom, right? So that's all this thing is saying is, again, I have one particle lives here, one particle lives here. I'm pasting these two things on top of each other and now increasing the overall dimensionality, which is why, again, if I think about particle 1 has only 2 basis functions. It's either plus or minus z. But if we go back to what we wrote down earlier, for this combination, we now have 4 basis functions because I need a number of basis functions, which is equal to the dimensionality of my space. So again, here I'm going from two-dimensional spaces to now a 4-dimensional space. Okay. Is that heavy? Sorry guys, give me just a second.
Ooh. That wasn't too heavy at all.
That wasn't too heavy?
Yep.
Did the battery die?
No.
Are you sure? Okay, let's find out.
Yeah.
Oh, don't pull them too far. You don't want to break my big stuff.
Okay.
Come on, mommy's computer. There we go.
Hey, Daddy, look.
What do you got?
This is the motor.
That's the motor.
Yeah, because I made a boat.
You made a boat.
Yeah.
Wanna walk around the robot?
It's speed.
Now plug that in, put those in. So I can finish talking. See. Sorry for all the distractions. It was Scheller's fault first. Okay. So good. So good. So again, so this is what this notation actually means. Now, I'm gonna plug it in. The headphones are right now.
Don't worry, Violet. We'll find whatever it is you need. Right on. This place is huge. So
You going to mommy, daddy's bedroom? Go, mommy, daddy's
I know that.
bedroom. Okay. Where'd my pen go? You guys say where I put my pen?
I think it was to your left, Professor, but I'm not positive of that.
Give me a second. Where did it go? Oh, there it is. It fell on the floor. Okay. So good. Now this notation, now that we're back on track, looks similar to the notation we saw before, which was what we wrote down SM, right? So this notation here looks similar to this notation here, but they're nowhere near the same thing. Okay, so this one again is talking about one state where you're talking about 2 eigenvalues for that particular state. For that state, right? So here, this is one state. This thing lives in one Hilbert space. So it's talking about the same state in the same Hilbert space, where now you're just specifying it by 2 eigenvalues instead of just 1, right? Where this state here is now 2 states, which is now described by basically 1 eigenvalue, technically 2, for each state. Okay. So again, this is 1 Hilbert space. This one is 2 Hilbert spaces pasted on top of each other. So even though this notation looks very similar to this notation, just don't be confused that they're telling you the same thing. Because again, this is now just saying I have what, 1 state in 1 Hilbert space described by 2 eigenvalues, where this one is saying I have 2 states in 2 different Hilbert spaces described by, in this case, technically 4 eigenvalues, right? 2 eigenvalues for each one, because remember, this is shorthand notation for this. So this is S1/2 and M1/2. S1/2 and M1/2 are the 2 different particles, but I'm just gonna put 1 eigenvalue for now. So again, we just have to be a little bit careful with that. Okay. Now from here, we can also expand any general state. So any general state can be expanded in terms of these 2 particle states, which basically means if I take this guy, I can now write this as a superposition over I and J of then AI for particle 1 tensor product. Let me get my tensor product. Cool. Let me write this the opposite direction, right? The way we're supposed to write it. So this is going to be AI for particle 1, tensor product with then a BJ particle 2 times then AI tensor product with then BJ for particle 2 state psi. Okay. Now again, this thing here is going to give me a complex number, complex amplitude, but this complex amplitude is going to depend on both I and j. So instead of this thing just being Ci, this thing's going to be Cij. So it's going to depend on both I and j. So this is now going to become the sum over Ij of the complex amplitude, which depends on both I and j, times then AI tensor product with then Bj. So this is actually the state, or if I wrote this in our more shorthand notation, this is then the sum over Ij of Ci Cj, AI comma Bj. So here, Cij is then equal to the inner product of AI Bj with psi, or this is AI1 tensor product BJ2 psi.
Could you back up just a second, Professor?
Sure. I wrote too fast as always.
Okay. That was all.
Sounds good? All right.
Yep.
So, good. So that's what this means. Now, another thing to note is that the AIs don't have to do anything with BJs. So, for example, particle 1 could be a spin 1/2 particle, where particle 2 could be a spin 4 particle. So they don't necessarily even have to have the same spin degrees of freedom. So again, AI here for particle 1 doesn't necessarily have to have anything to do with BJ2, right? So again, this may represent a spin 1/2 particle, where this one could represent something like, I don't know, a spin 1 particle or something like that. Spin 2 particle, spin 3/2, right? It doesn't matter. So these guys don't have to be in the same basis. They don't have to have the same spin. Again, this one may look at the SX components, where this one is looking at the SZ basis. It doesn't really matter. Okay. So they don't have to be the same. Now, typically when we write down our states, we're going to actually drop this tensor product, and we're going to know it's actually going to be implied, which basically means that, for example, when I write out the plus or minus z with the plus or minus z, even though this is technically equal to plus or minus z1 tensor product with plus or minus z2, we're usually just going to write this as plus or minus z1 plus or minus z2, okay? Just to make it a little bit easier to write the shorthand notation, instead of always writing that stupid tensor product, just to make it a little bit, a little bit briefer. So another thing we're going to do is we're going to define a little bit new states. So when I write ZZ, which again actually means Z1, Z2, let's for now just call that the one state. Okay. And then Z minus Z, which again is actually equal to Z for particle 1 minus Z for particle 2. I'm just going to call that the two states. Minus Z, Z, and so I get minus Z for particle 1, positive Z for particle 2 is equal to the 3 states. And then finally minus Z, comma minus Z equal to minus Z particle 1 minus Z particle 2. I'm going to call simply the 4 state for now. Okay. So that way we won't have to write all this stuff out over and over and over and over and over again. Okay. Good. How much time we got?
Almost 15 minutes, Professor.
Okay, good. So let's start our example. So let's start looking at an example on how all this stuff is going to kind of fit together. So the example we're going to look at is exactly what we were just talking about, which is the proton, the electron, the fact that this guy has a magnetic moment, the fact that this guy has a magnetic moment, which means we're going to look at the coupling between the magnetic field from the proton and the magnetic moment from the electron. So again, this is what's known as hyperfine splitting. So hyperfine splitting comes from the fact that, again, these guys have spins. These two spins from each one of the magnetic moments are basically got to couple with each other. That coupling then is going to give corrections to the energy. Right? So remember that for the hydrogen atom, the potential V of R is going to be equal to minus E squared divided by R, right? So this is the potential of the electron in the potential of that of the proton, okay? Also remember that for the ground state, then the hydrogen atom has energy En, which is equal to negative 13.6 electron volts divided by the principal quantum number N squared. Right? We'll derive this later, but hopefully you remember this from modern physics. If not, don't worry too much about it. Basically, as N increases, then this thing gets more negative, right? So here, N is equal to 1, 2, 3, blah, blah. Right? So it has to be a positive integer. There we go. Okay. So this is the ground state, ignoring all of these couplings. But again, the hyperfine splitting is going to come from the coupling between the, again, magnetic field or the magnetic moment of the proton with the magnetic moment of the electron. Right? As we also mentioned, again, the mass of the proton is, again, roughly about 2,000 times greater than the mass of the electron, which basically means that what? This is going to be a very small correction. So this correction will be very small. Hence, hyperfine. So it gives us a very, very tiny correction to the energy. So basically what happened is that the energies will split. So now there's actually going to be a new ground state energy, which isn't quite this energy. It's actually something slightly different than this, with then energies above this as well. Okay? So the ground state energy actually splits up into multiple different energies when you take this correction into account. But again, this correction is going to be a very small correction due to the fact of this. So we're going to get a very small correction on top of that. What is this? No, going. No, I want to do it. Now, there's also other corrections that we can talk about as well. So again, as I mentioned some of those earlier, some of them come from perturbation theory, from time-dependent perturbation theory. Some of them come from relativistic effects, all kinds of different stuff. We don't actually get to do those in this class, so we won't actually talk about them, but there's other corrections that you can look at as well. So good. So let's talk about the hyperfine splitting. So hyperfine splitting comes from, again, the Hamiltonian is going to be equal to then minus the magnetic moment of the electron dotted then with the external magnetic field at which it lives in, where that magnetic field comes from the proton itself. Right. Now, what we also know is, remember that the magnetic moment is equal to negative G times the charge, which in this case is going to be the charge of the electron, divided by the mass of the electron, all times the spin, right? The spin vector. So in this case, if we call, say, the electron particle 1, so this would be the spin components from particle 1, and then this portion will come from something similar from the magnetic field, which also is proportional to the spin of the proton, which we're going to call particle 2. So let's call this particle 2, this guy particle 1. Because again, the magnetic field is created from the magnetic moments, which means that it's also proportional to S2. Okay? So this means our Hamiltonian then is going to be equal to 2 times A divided by H bar squared times the spin vector 1 dotted with spin vector 2. Okay. So this is going to be our Hamiltonian. A is just going to be some sort of constant where this thing has units of energy. Right? So this thing is going to have units of energy, i.e. joules. We won't worry about what A is at this stage. Okay. So good. So because of this coupling, we're going to be talking about both spin states, which means our basis functions we're going to be looking at for this are going to be the 1, 2, 3, and 4 basis functions. Okay. So good. So the first thing we want to start looking at is what is this value here? So let's start looking at spin vector 1 dotted with spin vector 2. So let's figure out what this thing actually looks like and what is this thing. And I'm actually going to roll the 2 in here as well. I'm going to pull this 2 into that. So this is going to be 2 times then S1X. Do this a little differently. There we go. Right in the same notation I did before. So SX1 hat I hat plus SY1 J hat plus SZ1 K hat dotted with SX2 I hat plus SY2 J hat plus SZ2 K hat. So this is going to be equal to then 2 times SX1 SX2 plus, hey, what did you do that for? Plus SY1 SY2 plus SZ1 SZ2, right? This is what we get from the dot product. That's doing okay?
So far.
So now, but remember we introduced those raising and lowering operators that we had before. So remember that the raising and lowering operators were S plus minus were equal to SX plus or minus ISY, right? So here we can also have raising and lowering operators for each one of the 2 particles. So we can have S plus or minus 1, which is then equal to what? SX1 plus or minus ISY1. Then we're going to have an S plus or minus 2, which is then equal to SX2 plus or minus ISY2. You'll see why we actually want to do this in a little bit. Now, having said that, then our dot product of the 2S1 dotted with S2 vector, we can actually rewrite as S plus 1 times S minus 2 plus S minus 1 S plus 2 plus 2 SZ1 SZ2. So basically, if you use these definitions, put those into here, you'll actually get the original statement that what we had before. Is it okay?
Yeah.
Good. So the reason that we're going to do this is remember that's what? If I act S minus onto the state minus Z, that's going to give me 0. And if I act the plus state S plus onto the state Z, that also is going to give me 0. So basically what we're going to do is we're going to start acting these then onto states, right? Those states 1, 2, 3, and 4, where some of them are going to be destroyed. Because I can't raise them higher or lower in these cases. Okay. Guys doing okay? So now what we want to do is start looking for the matrix elements of the Hamiltonian. So let's look for the matrix elements of the Hamiltonian. Okay. So we should be able to get through this argument. So let's say I want to find the elements I, J with H, okay? Where again, I and J are gonna be two states, right? So not just one. I'm writing it, kind of looks like a one state, but remember this is a tensor product state together, okay? So let's put this in. So this is gonna be what? A divided by H bar squared times the inner product then of I with, so S, let's do it this way, plus 1 S minus 2 plus S minus 1 S plus 2 plus 2 S Z1 S Z2 J. Okay. Or we can write this as A divided by H bar squared times. So now I'm just going to sandwich each one of these individually. So I'm going to get an I S plus 1 S minus 2 J plus S, whoops, plus I S minus 1 S plus 2 J plus 2 times.
Daddy,
Yes, my son.
I'm getting bored just watching.
Okay, well, I only got a couple minutes left, and then when mommy gets home, we're gonna go get some lunch. Okay. Where do you want to go for lunch?
I don't know. Maybe it's a pizza.
We had pizza yesterday. We'll see. We'll talk to mommy.
Maybe. What else? What other restaurants?
We'll talk about it. Give me 1 second. Okay, so remember, these things are only going to act onto the Z components. So remember, each one of these guys now only acts onto a portion of that, which basically means that if I took S plus 1 acting on the states ZZ, this thing is only going to act on this portion of the states. Okay, which basically means this guy is going to raise him by 1. Which means it's going to destroy the states, where then if I act, say, S minus 2 on the states of, say, Z, Z, then that's going to lower only the second portion down. So this is going to be equal to then Z minus Z. Okay. So basically, each one of these guys can only operate then onto the portion of the state that belongs to them. So only belongs to their particular particle. So the 1 state can only act on the first one, and then the 2 particle can only act on the second portion of that state. Okay. Guys doing okay? Now, the other thing is, it can only act onto the M portion of the state, which means that we don't actually care about the S portion of the states. So I'm going to write this as M1, M2, right? So this is the magnetic portion of the first particle, magnetic portion of the second particle. State S plus 1, S minus 2. Then I'm going to write this as M1 prime, M2 prime, plus M1, M2, S minus 1, S plus 2, M1 prime, M2 prime, plus 2 times M1, M2, SZ1, SZ2, M1 prime, M2 prime, right? Because again, the raising and lowering operators only act onto the M component, so it doesn't do anything to the S component, so I'm not going to bother writing the S components. Okay. Good. Now again, what will happen is this portion is going to act on this portion, which is going to raise him by 1. This is going to act onto this portion, which is then going to lower him by 1. Okay. So that means if I was going to write this out, I'm getting an A over H bar squared times. So what will happen then is I get some component here. So this is going to be a C plus 1 component. And then I'm going to get a C minus 2 components. We call those primes because they're acting on the prime portion. And then I'm going to get the inner product of M1, M2 with M1 prime plus 1 with M2 prime minus 1. Right? So that's the inner product from this one. Here, again, this one's going to act on the first one, which is going to lower it by 1. This is going to act onto the second one, which is going to increase it by 1. So here I'm going to get a plus C minus 1 prime, C plus 2 prime. Then I'm going to get M1, M2 inner product then with M1 prime minus 1, and then M2 prime plus 1. Okay. But remember this bottom term here, the only thing when I add Z onto it, it just pulls out M1 and M2, right? Times an H bar squared, or times an H bar. So this last one is going to give me a plus 2 H bar squared M1 prime M2 prime times the inner product between M1 M2 with M1 prime M2 prime. Okay. Now, what's the point of all this? The point of all this is that this term here and the second term both give me off diagonal terms, right? Because again, I'm going to get a delta product between M1 and M1 prime plus 1, and then also a delta product between M2 and M2 prime minus 1. So this is an off diagonal term. This one is also an off diagonal term. The only diagonal term then comes from the third term, which has to do with the SZs. Okay. So basically, my diagonal term is only going to be this term, while my off diagonal terms are going to be these guys. Okay. Now, I'm out of time, so I'll stop there. We'll pick up with this Tuesday. Okay.
Officially out of paper in this notebook, Professor.
Alrighty, huh? We're about halfway through. Nice. Nice.
Yeah, you just filled up that section.
Very nice. So you'll have to spend a couple bucks and get another notebook. Or use old.
That's what I'll probably do. Yeah. So the homework is essentially due next Thursday. For sure. This kind.
Yeah, but if you have anything between, so if you have anything on tomorrow or Monday, you can give it to me then. Just stop by
Okay.
with me. Otherwise, yeah, I'll just collect everything from you guys on Thursday.
Okay. I won't be on campus tomorrow, so we'll have to.
Okay. Gotcha. Yeah, so if you have anything on Monday, then yeah, you can drop it off. Otherwise, yeah, I'll just collect everything from you guys on Thursday. So.
Okay.
Alrighty. Good. Good.